Let's begin with a simple image. A spinning top. You wind it up, let it go, and it twirls, balanced on its tip. This is classical angular momentum, a familiar concept. We've all seen it in action. In spinning planets, pirouetting dancers, or orbiting satellites. But now imagine something strange. Imagine a particle, something so small that it defies visualization, like an electron. Now try to imagine that spinning. This is where classical physics begins to fail, and quantum mechanics enters the scene. A world where spinning doesn't always mean motion, and logic must bow to probability. Welcome to the bizarre, beautiful concept of spin-angular momentum. Angular momentum in classical physics is simple. It's the product of a particle's moment of inertia and its angular velocity. In equations, we write it as L equals I times omega, where L is angular momentum. I is the moment of inertia, and omega is angular velocity. But in quantum mechanics, angular momentum is quantized. It comes in discrete chunks, just like energy levels in atoms. And here, spin, the intrinsic form of angular momentum, emerges as a property with no direct classical analog. Unlike orbital angular momentum, which results from particles moving in space, spin is inherent to particles. An electron doesn't need to orbit anything to possess spin. It just has it. But what does that even mean? The year is 1922. German physicists Otto Stern and Walter Gerlach conduct an experiment that would puzzle and fascinate generations of scientists. They fired a beam of silver atoms through a non-uniform magnetic field, expecting the atom's angular momentum to deflect the beam into a continuous smear, as predicted by classical physics. But instead, the atoms split cleanly into two distinct paths. Something was wrong. Or maybe something was right that nobody had predicted yet. What they observed was an orbital angular momentum at work. It was spin, an entirely new property of matter. Spin is quantized. An electron's spin can only take on two values when measured along a particular axis. Either spin up or spin down, that's it. No in between. Mathematically, spin is described using special matrices developed by Wolfgang Pauli, called Pauli spin matrices. These act on mathematical objects called spinors, which encode the probabilistic nature of spin. Spinors are strange. Rotate them by 360 degrees, and they don't return to their original state. They actually flip sign. Only after a full rotation of 720 degrees do they return to their original configuration. This behavior defies our everyday experience, but it's real, verified, tested. Spin is not like a spinning top. It's a quantum number. It's a fundamental characteristic, just like mass or electric charge, and it's built into the very identity of a particle. In quantum mechanics, angular momentum is described by two quantum numbers. The first is the total spin quantum number, denoted by the letter S. The second is the magnetic spin quantum number, denoted by m sub s. For electrons, the value of S is 1/2. That's why they are classified as fermions. Fermions obey the Pauli exclusion principle. No two fermions can occupy the same quantum state at the same time. This is the reason atoms have structure, why the periodic table exists, and why matter doesn't collapse into a single point. Particles with integer spin, like 0, 1, or 2, are called bosons. They do not follow the exclusion principle. Instead, they can occupy the same state in large numbers. This leads to phenomena like lasers and Bose-Einstein condensates. So spin doesn't just define a property, it defines the behavior of matter. In quantum mechanics, every measurable quantity corresponds to an operator. Spin is no exception. For spin 1/2 particles, We define spin operators using the Pauli matrices. These are: the spin operator in the x direction is equal to h bar divided by 2 times the sigma x matrix. The spin operator in the y direction is equal to h bar divided by 2 times the sigma y matrix. The spin operator in the z direction is equal to h bar divided by 2 times the sigma z matrix. Here, h bar is the reduced Planck's constant, and the sigma matrices are simple 2 by 2 matrices that define the spin behavior along each axis. When you measure the spin of an electron along the z-axis, the only possible outcomes are positive h bar divided by 2 or negative h bar divided by 2. You can't predict which one you'll get. You can only assign a probability, but the result will always be one of these two. Nature doesn't allow for anything in between. And if you then measure the spin along the x-axis, the answer will again be either positive h bar divided by 2 or negative h bar divided by 2, but now with equal probability. Even if you just measured it along the z-axis, the act of measurement changes the system. This is the core of quantum mechanics. Spin isn't just an isolated property. It becomes even more strange when entanglement is involved. Imagine two electrons born from the same event, say, the decay of a neutral pion. Their spins must be opposite. One is spin up, the other spin down. But until we measure, we don't know which is which. Measure one, and instantly the other is determined, even if it's light years away. This is quantum entanglement, and it has been tested, confirmed, and used. Even in quantum communication systems today. Einstein called it spooky action at a distance, but experiments have proven it time and again. Spin lies at the heart of this quantum mystery. Spin isn't just abstract, it's practical. In magnetic resonance imaging, or MRI, the spin of protons in your body is manipulated by magnetic fields and radio waves to produce detailed images. In quantum computing, quantum bits, or qubits, are often built from spin states of electrons or nuclei. The two-level system, spin up and spin down, forms a perfect quantum bit. In spintronics, researchers are developing electronic devices that use spin, not just electric charge, to process information. This could lead to faster, more efficient computers. And in astrophysics, the spin of black holes affects how they warp space-time and devour matter. Spin is embedded in everything, from the tiniest particles to the fabric of the cosmos. Why do fermions obey the exclusion principle while bosons don't? The answer lies in the spin statistics theorem. It tells us that particles with half-integer spin must follow Fermi-Dirac statistics, while particles with integer spin must follow Bose-Einstein statistics. It's not just a coincidence. It's a deep law of quantum field theory. Break this rule, and you break causality itself. Spin determines whether particles build the structure of matter or form the force-carrying fields of the universe. Many students struggle with the concept of spin because it's so counterintuitive. So let's be clear. Particles do not physically spin like tiny spheres. That image is misleading. Instead, spin is a form of angular momentum that emerges from deeper symmetries of space and quantum fields. It's described using group theory, specifically using the mathematical group called SU2 for spin 1/2 particles. This mathematics isn't just for show. It matches experiments to extraordinary precision. When you hold a magnet in your hand, you're feeling the cumulative effect of countless electrons aligned in the same spin state. When you look at the periodic table, its structure is dictated by how electrons fill orbitals according to their spin. The matter that forms stars, planets, and life. All of it is governed by this strange quantum property, and the more we study it, the more we realize that spin is not just a characteristic of particles. Spin is a cornerstone of quantum reality. So, next time you hear the word spin in quantum mechanics, don't think of something turning. Think of something fundamental, irreducible, a quantum fingerprint that shapes the entire universe.